me introduce Chris Beem from Oxford. Today he'll be talking about Hall-Littlewood chiral rings and derived Higgs branches.
Okay, so thanks, Tutor, and thanks to all of the organizers for letting me give this talk. And yeah, so Tutor read the title, and I should mention at the outset that this is going to be about some work which has been ongoing for a little while, has yet to appear with my graduate student, Diego Berdeja Suarez. So the context for the talk and basically everything I do is supersymmetric and more specifically superconformal quantum field theories. And these are, from a mathematical point of view, many things, but in particular, they have sort of an algebraic and a geometric side. Here is some silly cartoon to illustrate this truism. So superconformal field theories have sort of various lives depending on your way of looking at them. And at least two popular perspectives are sort of a geometric point of view, which you might, roughly speaking, associate with studying moduli spaces of vacua of these theories. And they have a more algebraic life, which maybe is more associated with what these days would be called a conformal bootstrap point of view, where you think about them in terms of local operators that have some algebraic structure. And a general principle that I think is interesting is that there should be some sort of useful, interesting dialogue between these perspectives. This isn't a new idea. There's many examples that are well understood and well studied, but I think that there's a lot there and it's worth sort of pushing in all possible directions. And I'm going to be talking about one little development in this area that I think nicely illustrates this kind of algebraic geometric interplay within the context of superconformal field theories. And I'll specialize in a moment. So more precisely, I'm going to be talking about four-dimensional n=2 superconformal field theories. And to jump ahead, the main geometric aspect that I'm going to be interested in these theories are their so-called Higgs branches of vacua, and I'll give a review for people who don't spend their lives with these things. So from a superconformal field theory or sort of operator algebra bootstrap perspective, it is natural to study the Higgs branch of vacua and more general moduli spaces of vacua as algebraic varieties in terms of their rings of functions. That's a natural way to study spaces anyway, but it sort of presents itself to you in this way in an SCFT context. But the main point I'm going to be making in this talk is that in a certain sense, if you follow the guidance of the superconformal field theory, which you should always do, this is sort of not the right object to study. Or at least I'm going to be arguing that there's a sense in which it's not the right object to study. There is a better thing, which for some historically contingent reasons is currently going by the name of the Hall-Littlewood Chiral Ring, but I'll explain what it is. And from a geometric point of view, saying that you should think of the Hall-Littlewood Chiral Ring instead of the ring of functions on the Higgs branch turns out to mean that you should treat the Higgs branch as an affine derived scheme. I say that phrase somewhat warily, as there are surely multiple people in the audience who really know what that means, and I only sort of know what it means. But nevertheless, that's the point I'm making. And from a more physical point of view, saying that I should study the Higgs branch in this modified way roughly corresponds to saying that I should keep track in a particular way of residual abelian gauge symmetries that are preserved in generic Higgs branch vacua. And I'll expand on this for people who don't speak this language. And a few interesting technical observations that I'm just forecasting here in case I don't sort of get through the talk in a totally coherent way, is that some nice observations are that these Hall-Littlewood Chiral rings, these sorts of Higgs branch chiral rings on steroids, they can exhibit additional symmetries compared to the usual Higgs branch symmetries, which are somewhat mysterious and interesting physically. There's some way that this whole story is a chapter in a more general argument that one should make, which is that we should think of the moduli space of vacua of a quantum field theory more holistically and not just focus on the Higgs branch or other branches. And although I won't return to this at any level of detail, an underlying motivation for this story is that there's an interesting relationship between these Hall-Littlewood Chiral rings and the vertex operator algebras that are associated to four-dimensional n equals 2 SCFTs, which has been another subject that I've worked on quite a bit. Okay, so that's the narrative. In case you don't want to pay attention to any of the details. And here's my plan. So I'm going to start with some sort of a review of these four-dimensional supersymmetric quantum field theories and the relevant aspects of their moduli spaces of vacua. And then I'm going to get into a discussion of things that are attached to the phrase Hall-Littlewood. I'm going to point out some connection with derived algebraic geometry and derived symplectic reduction that will be understandable to people who don't know what derived algebraic geometry is, because I'm sort of one of those people. And then I'm going to try to interpret some of the structure from a more geometric and physical point of view. At the end, I'll say something about a class of examples that demonstrate some, I think, interesting general properties of what's going on. But it's going to be a sort of fast discussion of the examples because most of what there is to say about them is very technical, and then there's just some answer that I'll summarize. Okay. Let's see. Okay, so I want to say something about four-dimensional n equals 2 superconformal field theories, which are the appropriate setting for this story. And to start with, because it helps sort of give at least in a sort of high-level abstract way, a large class of examples that one cares about, I want to talk about the way that one writes down Lagrangian quantum field theories with this much supersymmetry. So the main ingredients are the free field supermultiplets, the vector multiplet, and the hypermultiplet. So if I have a gauge theory, then there's a gauge group G, and I have a vector multiplet, which is a scalar, a set of Weyl fermions named lambda, and a gauge field, all in the adjoint of that group. And then I introduce matter, which comes in the form of these things called hypermultiplets, which are labeled by a quaternionic representation of G. Often that quaternionic representation is a complex representation, direct sum, its complex conjugate, but it could be some intrinsically quaternionic representation. And with those ingredients, one can phrase what one needs in order to be studying a superconformal field theory instead of a generic classical field theory or some field theory with non-trivial renormalization group properties. The gauge group G needs to be semi-simple. So no U1s. There's a condition for the vanishing of the beta functions of the gauge couplings, which is the real meat of what you need in order for it to be a conformal theory. And although I'm not going to return to this equation in any detail, there's some precise characterization of what sorts of matter representations are allowed in order to have conformal invariance be preserved. So the dual Coxeter number of each semi-simple factor has to be equal to some sort of combination of indices of the representations that are appearing. And that's it, except for gauge couplings. So if one is a more creative quantum field theorist, there are other things that you can do. You can introduce mass parameters and things that will make your theory more interesting. But I like conformal field theories, and in a conformal field theory, the Lagrangian is completely fixed by the requirement of superconformal invariance up to the value of complex gauge couplings. So there's a complex coupling for each simple factor in the gauge group, and that's all I get to choose. There's some analog of all of this in not necessarily Lagrangian theories. Again, I'm not going to go into detail and examples, but I just want to mention that there's some relationship where you replace these indices of your representations with some anomaly coefficient associated to a potentially not Lagrangian building block that you're using to build a more general gauge theory. Okay, so that's all to give some sort of background where you believe that there's a general story here, if this isn't what you usually study. But I'm going to be focusing not on sort of the full field theoretic dynamics of these theories, but on their moduli spaces of vacua. These can be sort of complicated. In general, the moduli space of a 4D n equals 2 theory is partitioned into various things people call branches. And there are 3 types of branches. There are Coulomb branches, and you can think of these as vacua where the scalar in the vector multiplet gets a non-trivial expectation value, but the scalars in the hypermultiplets all have 0 expectation value. If you don't like a Lagrangian language, these are the vacua where the U1R symmetry of the n equals 2 theory is broken, but the SU2R symmetry is unbroken. And although I'm not going to be talking about Coulomb branches, they are an interesting subject, and they're the place where you run into so-called special Kähler geometry, and this is the domain of Seiberg-Witten theory, and it's a deep subject. More of interest to me is going to be the Higgs branch of vacua. So this is sort of the opposite sort of vacuum, where the hypermultiplet scalars get vevs, the vector multiplet scalars don't, and which R symmetries are broken are flipped. And abstractly speaking, these Higgs branches are some sorts of canonical hyperkähler, singular conical hyperkähler spaces. They can be algebraically quite interesting. They have the virtue that if you have a Lagrangian description, they're described classically exactly, so you don't need to know about quantum corrections in order to characterize these things. But in non-Lagrangian theories, these things can be still quite hard to get your hands around. And then there's a thing called a mixed branch, which is where both types of scalars get expectation values and both types of R symmetries are broken. I don't think it's too strong to say that there hasn't been so much work on the general story of mixed branches, although that's not to say that there hasn't been interesting work, including some by people in the audience. But it hasn't been as much of a story as these first 2. So I want you to have a cartoon in mind about the structure of these moduli spaces, because it's going to end up sort of coming back to us later on. So if you're like me, then for the first 5 years that you think about n equals 2 superconformal field theories, you think about this picture in the top left, where there's a Higgs branch, which is some sort of an interesting conical shaped thing, and I don't know how to draw fancy things, so I just draw it as a wedge. And there's a Coulomb branch, which is some sort of boring, roughly affine thing, and they meet at a point, which is the vacuum where conformal invariance is restored. That's not the generic case, because in that case, you have a Higgs branch and Coulomb branch and no mixed branch. In the generic case, and of course, this is a cartoon, so I can't really draw what's generic, where things are going to be very high dimensional. But in the generic case, you're going to have mixed branches, which means there's going to be some sort of subspace in the moduli space of vacua where you're sort of, it's this green subspace where you can sort of move in the Higgs directions and the Coulomb directions at the same time. And this will intersect both the Coulomb branch and the Higgs branch along some sort of singular subloci inside of those spaces. Then there are a couple of extra pictures that I need to draw because they're really going to be, well, the bottom right-hand side is really going to be what we run into later. So an extreme version of this mixed branch scenario is when either the entire Coulomb branch sort of is embedded smoothly inside of some mixed branch, and this situation has been dubbed an enhanced Coulomb branch by Phil Argyres and Mario Martone and their collaborators. And there's a sort of opposite notion, which I don't know if it's been named in the literature, but it should obviously be called an enhanced Higgs branch. And that's the case when the entire Higgs branch, which in this picture, in order to demonstrate this phenomenon, I've had to collapse the Higgs branch to just look like a line, but where the entire Higgs branch is embedded smoothly inside of some mixed branch. And so the physics of that is that you're saying that if you go to the generic points on the Higgs branch, then there are still Coulomb branch directions you can move in, which is to say that there are still abelian gauge theory degrees of freedom in your theory. So there's some scalar in an abelian vector multiplet whose VEV you can turn on, even when you're in a generic Higgs branch. So you Higgs the theory as much as you can by turning on as many matter VEVs as you can, but you still haven't managed to kill all of the gauge symmetry. And so there's still more directions that you can move in sort of Coulomb branch directions. Okay, so all of these things can happen, but I think it's useful to have this sort of cartoon of the spectrum of possibilities to think about, what aspects of this potentially very large and intricate moduli space structure you might get at with different algebraic ingredients. Oops. Okay. So that's a cartoon. We can, or I should say a little bit more about the structure of these Higgs branches beyond cartoons. So in gauge theories, the Higgs branch is realized as a hyperkähler quotient, which goes like follows. So take a vector space that carries this quaternionic G representation that I specified in defining my theory. I think of this vector space as constituting the possible expectation values for the scalars in the hypermultiplets. There's a hyperkähler moment map, which is a triplet of moment maps for the G action on this space. And the hyperkähler quotient corresponds to setting all of those moment maps equal to 0 and taking G orbits. So in physics terminology, you're setting D term and F terms equal to 0 and dividing by the gauge action on the space of hypermultiplet expectation values. And this generalizes to theories that don't necessarily have a Lagrangian description, where instead of having this vector space VR to begin with, you have the Higgs branch of some theory that might be sort of an irreducibly interacting non-Lagrangian theory, but that has a hyperkähler G action on it. And so therefore has a hyperkähler moment map, and you can set that equal to 0 and take the G orbits. That's the story in the world of hyperkähler geometry. It's going to end up being the case that the story I'm telling is more from the perspective of complex geometry. And so from the perspective of a fixed complex structure, or equivalently from the point of view of a given choice of n equals 1 subalgebra of the n equals 2 superalgebra, you can think of these as being complex algebraic singularities, which are actually holomorphic symplectic. So they have a non-degenerate 2-0 form on their smooth locus. And then this description of gauging, instead of phrasing it as hyperkähler moment maps and hyperkähler quotients, you can introduce a holomorphic moment map, which if you're working in the first complex structure means that you're taking the second plus I times the third of these moment maps that were previously in a 3-component vector. And you set those equal to 0 and then do the symplectic, the Marsden-Weinstein quotient with respect to G. And just as a remark, in superconformal field theories where I don't allow myself to turn on other parameters that break conformal invariance, 0, and this 0 is this 0, the 0 where I'm looking at the zeros of the moment maps. It's always an irregular value of the moment map. And so what you get when you do this is not a smooth holomorphic symplectic manifold, but some kind of a stratified holomorphic symplectic space. At the very least, you're going to have 2 strata, one of which, if we go back to this cartoon I had, at the very least, you're going to have 2 strata where one is the point at the tip of the cone, which is the singular point, and the rest is some sort of smooth rest of the space. But really, you can have all sorts of intermediate strata. Okay, let me get back to where I was. Okay, so that was a very fast review, hopefully at least getting sort of a cartoon picture of what's going on, both sort of generally and in the case of Higgs branches. I now want to tell most of the same story in this more algebraic SCF, what I would call SCFT language, so sort of conformal bootstrap language, if you will. So here, the primary protagonist is the symmetry algebra. So if I have n equals 2 superconformal field theory, the complexified symmetry algebra is the superconformal algebra SU4/2, which has some subalgebras that many people will recognize. So the bosonic subalgebra of this thing looks like SU4 times SU2 times U1, which contains a subalgebra, which is the one that we usually think about in physics, which is dilatations or dilations, and spin in 4 dimensions, which is SU21 times SU22, and then R symmetries, SU2 capital R and U1 lowercase r. And these symbols are going to be appearing later on. We have some standard expressions for both the Cartan generators of those subalgebras, and I will overload the notation, so these will also denote the eigenvalues of various objects under the action of those Cartan generators. I see a question, but I think Jacques has answered it.
Do you want to elaborate on that briefly?
I agree. I agree with Jacques. There's a C star action. So these are conical spaces that have C star actions. In the case of the Higgs branch, you have this hyperkähler space, but you have the SU2R symmetry is always an actual symmetry of the theory. And that means that the space looks the same in every complex structure. More generally, you can have hyperkähler spaces that look different in different complex structures. So maybe that would just be one additional comment. Now, in addition to even generators, there are odd generators of this superconformal algebra, which usually are called Q's and S's. Q's are the Poincare supercharges that I would have in a not necessarily conformal theory. The S's are there because it's a conformal theory. And these things transform in doublets of the various rotation generators and the SU2R symmetry. And then once you have this big symmetry algebra, you get to a priori organize the complete set of local operators in your theory into some sort of nice irreducible representations of the symmetry algebra. They should be unitary with respect to an appropriate notion of Hermitian conjugation on this algebra. which I'm not making explicit here because I'm working with everything complexified. And the general structure of these is that you have a so-called superconformal primary operator. I didn't label it on here, which is this O, which will be labeled by its eigenvalues under these various Cartan generators I introduced up here. And then you act with all of the generators of the algebra and you fill out a full representation. And the main thing to think about is acting with the Qs. So these Qs and Q tildes give you the superpartners of this superconformal primary. And generically, you can act with 8 of them to get different super descendants. So if you can act with all 8 and get things that are non-trivial, then you're dealing with a sort of generic or what's sometimes called a long representation of this superconformal algebra. But for certain special representations, which are sometimes called short or semi-short or BPS representations, there will be some combinations of these supersymmetry generators that non-trivially annihilate the superconformal primary. And in this case, you have sort of a smaller representation, and these end up being the ones that are interesting from the point of view of sort of exact supersymmetric physics that one can do with these theories. The other operators are very interesting too, but they're not what I'm talking about. And the full set of these local operators form some sort of an intricate algebraic structure that at least I call an OPE algebra, but lots of people call it that too. And this is a complicated sort of algebra that knows about the full glory of conformal field theory, and it involves taking operators that live at different points in space-time and letting them get close to each other. And this is generically a singular operation. And so you need to look at sort of the various terms that appear with different strength singularities when you try to take that collision limit. There's a whole story there, but the virtue of studying special operators that live in special representations will be that we can extract simpler algebraic structures that sort of have a more transparent relationship with geometry. So in this abstract setting, I advertised at the beginning of the talk that we encounter the Higgs branch as a complex algebraic variety defined by its coordinate ring. And the way that that works is the following. A general so-called unitarity bound implies that for any of the allowed representations of the superconformal algebra, you always have the conformal dimension, this number delta, which is the eigenvalue of the dilatation operator, is bounded below by twice the SU2R charge. And for the operators that saturate that inequality, one can show that you necessarily have that the U1R charge and that the spins are 0. So these are scalar operators. They live in operators obeying these conditions are necessarily the superconformal primary operators in a particular type of representation that in a notation introduced by Dolan and Osborne, which is the one I like, are called B hat R multiplets, but you shouldn't worry what it's called if you're not already someone who loves superconformal representation theory. And these are half BPS multiplets in the sense that this operator this putative operator that obeys these conditions on its quantum numbers will be annihilated by the action of 4 different Qs, the Q1 alphas and the Q tilde 1 alpha dots, where alpha is plus or minus and alpha dot is plus dot or minus dot. So there are 4 of those. And it follows from simple selection rules that I won't review, that these operators have non-singular operator product expansion. So you can bring them on top of each other and nothing goes wrong. And so you can define an algebraic structure by defining the product of these operators literally to be what you get when you have them sitting literally on top of each other. And this gives them the structure of so this gives the set of operators that live in these as superconformal primaries of these B hat R multiplets, the structure of a commutative associative C algebra. And this is the so-called Higgs chiral ring. And in Lagrangian theories, one can observe, and I'm going to review part of the observation momentarily. And more generally, it's actually, I think, just a conjecture, but it's something I'm pretty sure everyone believes is true, that this ring is the coordinate ring of the Higgs branch of vacua of the theory. So the Higgs branch of vacua is defined in a different way. It's not, this MH is not defined this way if you're a physicist. It's defined as the set of zero energy configurations of your theory where SU2R symmetry is broken and UNR symmetry is not broken. And this equality is a conjecture that everyone believes to be true. And a remark that I would like to make here, just because it's something that wasn't clear to me for a long time, is that from this algebraic point of view, it's actually not totally obvious where you should see the symplectic structure on this space coming from. And I know of an algebraic derivation, but it's very complicated and involves a lot of other technology. And I don't know of a simple derivation. Nevertheless, this ring is actually a Poisson algebra with a holomorphic Poisson bracket that corresponds to the symplectic structure on the Higgs branch. Okay, and now, so now I want to review how you realize the hyperkähler quotient structure that takes place when you gauge from this algebraic point of view. This is standard, but also sets the stage for the elaboration that will appear momentarily. So if I have a theory with a G symmetry that I'm planning on gauging, yes, question, doesn't R Higgs have a natural non-commutative deformation? R Higgs has a natural commutative, non-commutative deformation in 3 dimensions. Davide might know about a natural non-commutative deformation that you see in the 4-dimensional case, but I only know how to get it by going through a vertex algebra, which is more than I wanted to talk about here. So here I'll be speaking to a certain subset of the audience who knows a bunch about this stuff already, but part of the story of what's happening here is that even though many of us know well that Higgs branches sort of persist across dimensional reductions, and sort of the Higgs branch of a 4D theory looks similar to looks identical to the Higgs branch of a theory you get in 3D if you reduce on a circle. Maybe you can even lift up to 5 dimensions. Some of the extra structure that is sort of natural from a physical point of view seems to depend on how many dimensions you're working in when you look at it. And so the story that I'm telling today is really a 4-dimensional story. And it won't have a 3-dimensional or 5-dimensional analog that I'm aware of, even though the Higgs branch is sort of a thing that lives all over the place. Okay. So right, if I have some abstract theory as my starting point that has a G symmetry that I'm planning on gauging, then for physics reasons, there will be a conserved current operator, which is the current whose corresponding charge measures G charges. And by superconformal representation theory, that thing has to live in a B hat 1 multiplet, which means you get one of these Higgs branch operators from it, which gets identified with the holomorphic moment map of the G action on the Higgs branch of the original theory. When you gauge, what happens is that holomorphic moment map becomes a Q variation of the gauginos in the vector multiplets that you introduce. So previously you had that moment map as a special short multiplet in your theory. And then when you turn on the gauge coupling, this moment map operator combines with another operator that you've introduced, this Gaugino operator, so that it no longer obeys the correct shortening conditions to be one of these B hat1 operators. And so what that does is that at the level of this ring of operators, and as these B hat operators, you quotient by the ideal generated by this operator that's the moment map. And when you further restrict to gauge invariance, you're exactly getting the Higgs branch chiral ring of the gauged theory is the G invariance of this quotient, which is the same thing as the hyperkähler quotient because symplectic quotient is the GIT quotient. So if you look at the space defined by this quotient, then that's going to be the same thing as the symplectic quotient of the zeros of the complex moment map, which we reviewed above, is the same thing as the full hyperkähler quotient. So you sort of rediscover a little bit of geometric invariant theory from a physics point of view when you do this exercise. Okay, and now I want to make what I guess is the main point, which is that, so this is either an argument or an assertion or philosophy, but I would say experience leads one to believe that interesting algebraic structures in supersymmetric quantum field theory, I wrote often here, but I really want it to be always in some sense, arise as some kinds of categorifications of numerical invariants that are computed by the path integral. So this is something which is true in lots of examples. There are things called BPS partition functions, vortex partition functions, superconformal indices. The thing that we really love to do with superconformal field theories is compute some path integral. And frequently when you do the path integral, you construct some numerical invariant, which is counting something which you want to be sort of you want to be counting something about the vector space underlying these algebraic structures. Okay, that's super vague, but let's see where it takes us. The Higgs branch chiral ring is the categorification that it's a little bit silly for me to be using this language because it's not actually that fancy, but I've been trained to use this language by some of my friends. So the Higgs branch is the categorification of a particular algebra, or of a particular nice sort of generating function, which is its Hilbert series. So it's a graded ring. And so you can define its Hilbert series to be the generating function this way, the generating function of the dimensionalities of the graded components of the vector space on which this algebraic structure is defined. And given this simple observation, a reasonable question is whether our superconformal field theory wants us to study this particular quantity. It's well defined because the ring is well defined, and so this Hilbert series is well defined. But it would be nice if that Hilbert series was something that I could compute by, or that I could define as some sort of path integral of my four-dimensional quantum field theory on some background. And the place to look for that, I claim, is in the world of superconformal indices. So superconformal indices are a class of partition functions for superconformal field theories that count various nice subclasses of representations of the superconformal algebra that appear in its spectrum of operators. And from a path integral point of view, these correspond to some sort of S3 times S1 partition functions, where you're counting states in the Hilbert space that your theory assigns to the S3, which are the same things as the local operators in your theory due to the operator state correspondence. Okay. So that path integral computes the so-called superconformal index, which I've written down in its most general form here. So it computes a supertrace over that Hilbert space assigned to the S3 of, okay, this is some generating function of multiplicities where you weight things by powers of P, Q, T, and X, where P, Q, and T are raised to powers that observe the charges of your operators under my various Cartan generators of the superconformal algebra, and I can also include some extra parameters to measure charges with respect to global symmetries. Okay, this is, no one who doesn't already love superconformal indices should pay much attention to this actual expression. What's important is the next set of statements, which is that you can classify the different ways that you can specialize the index by taking various limits of the parameters involved, these P's, Q's, and T's. You can classify the ways that the index can simplify so that it counts a more special subset of the operators in your theory than the generic case where you're counting 1/8 BPS operators. So things that are annihilated by a single Q. So this was done by Leonardo Rastelli and collaborators 7 years ago now. And here's a little flow chart of the specializations you can do. Some people know some of these limits and they love them for various reasons. If you don't, the important thing to know is that none of these limits are guaranteed to give you back the Hilbert series of the Higgs branch chiral ring. This can be contrasted with the case of three-dimensional n=4 theories. In three-dimensional n=4 theories that also have Higgs branches and also have Higgs branch chiral rings, there is an analogous thing called the superconformal index, which is an S2 times S1 partition function. And you can take a limit of that so that you get on the nose the Hilbert series of the Higgs branch. So the 4D theory feels differently about the Higgs branch chiral ring than the 3D theory. And this observation and some aspects of it were explored by Shlomo and Brian 6 years ago. And I want to argue that morally the message here is that the Higgs branch chiral ring isn't the right thing to study from a four-dimensional SCFT point of view. If it were the right thing to study, the theory would want to hand us its Hilbert series. This limit in my flow chart, which is the so-called Hall-Littlewood limit of the superconformal index, is almost doing what we want. There's a question, is R Higgs a graded ring? It is a graded ring. Is M Higgs the homogeneous spectrum approach? No, M Higgs is just spec. It's an affine thing. Right, so there's this limit called the Hall-Littlewood index, which is almost trying to count Higgs branch chiral ring operators. So it's almost trying to give me the Hilbert series of the Higgs branch, but it doesn't quite do it in general. Here's precisely what it gives me. So the right-hand side is not being defined as a limit here, but this occurs as a limit starting out with the original index. It is counting a supertrace over a subset of operators in my theory, the Hall-Littlewood subspace, which are states whose conformal dimension, whose scaling dimension is not equal to 2R, which was the case for Higgs branch chiral ring operators, but is equal to 2R minus lowercase r. And additionally, these are states that are in the singlet representation of the left-handed SU2. So this is what it's, so you can do a little bit of superconformal indexology. Is the Hilbert series, can you remind which is Q, which is T? Sorry, I'm just catching up. I'm not, Sorry, what is the question about Q and T? What the actual expression in the index is? This is the expression. There are various conventions in the physics index literature about how to parameterize these fugacities. You can redefine them in different ways. Is the Hilbert series supposed to be modular? I don't think so. There's another index called the Schur index, which I love even more, and that is modular because of a connection with vertex operator algebras. Sorry, where was I? Okay, so the thing that you get out of a limit of the index is something which is counting operators that obey these three relations for their quantum numbers. Oh, I made the same mistake previously. This E is supposed to be a delta. Some people call scaling dimension E. So the first two of these conditions characterize what are normally called n equals 1 chiral ring operators in these theories. And the third condition is an additional condition that gives you some subset of n equals 1 chiral ring operators. And you can now open your favorite reference on the full set of unitary irreducible representations of these superconformal algebras and go look for operators that obey these conditions. And sure enough, the B hat multiplets, the ones that gave us these Higgs branch operators, are there. But there's an additional ingredient which have an even, well, equally opaque naming convention, which are so-called D-bar multiplets. So there's a single other class of superconformal representations that are labeled by an R charge and a spin, who contribute operators to my theory that are counted by this limit of the index. It's actually not the superconformal primary of these D-bar multiplets, it's a descendant, but that's not important. And the things that contribute are then annihilated by 3 supercharges instead of 4. So the Higgs branch chiral ring was a half BPS object. And if I include these D-bar multiplets, I have a 3/8 BPS structure. And okay, there's not much you can do with those names if you're not already into that sort of thing. So you get some intuition from looking at free Lagrangian gauge theories, where the things that give you these D-bar multiplets are precisely composite operators that you'd be able to use in the hypermultiplet scalars. Those were the things that would give me Higgs branch chiral ring operators, as well as particular components of the gauginos, the right-handed gauginos that live in the vector multiplet. So it might not be totally obvious that you should choose this this specific subset of elementary fields in your Lagrangian theory to build sort of a preferred substructure in your operator algebra, but this is what we're being told. And these operators also have non-singular coincident limits. And so they define a supercommutative associative C algebra, which is now the thing that's being called the Hall-Littlewood Chiral Ring. And the naming here is that it's inherited from this limit of the superconformal index that was named the Hall-Littlewood index by Leonardo and his collaborators for other reasons. So we can observe some structural properties. This is a doubly graded supercommutative C algebra, graded by capital R and let's say negative lowercase r in order for it to be non-negatively graded with respect to both. The Grassman parody is lowercase r mod 2. The lowercase r equals 0 component is exactly the Higgs branch chiral ring. So this is some sort of extra structure that lives at sort of higher U1R charge than the Higgs branch chiral ring. There are some extra structures that require more technology to show that they're true. So this structure inherits the Poisson bracket that you had at the level of the Higgs branch chiral ring. It's also independent of the gauge coupling, just as the Higgs branch chiral ring was. And to show these, at least for me to show these facts, I need to introduce some of this extra vertex algebra structure that I'm eliding for this entire talk. Okay, so that's a thing that exists abstractly in a superconformal field theory, and I'm claiming that it should be the thing that replaces the Higgs branch in our mind. And we get a sense of what's going on if we look at how this structure behaves in gauge theories. So I want to follow a little bit the approach I was taking before when I was looking at how the hyperkähler quotient appears. So I want to imagine that I start out with a theory for which I know, oh, sorry, this should say, for which I know the Hall-Littlewood chiral ring. And I want to gauge a G symmetry, and I'm going to assume it's one of these symmetries that I can gauge in a way that's consistent with conformal invariance. And I'm going to do this very idiosyncratically in two steps. I start out with my theory that I named T. And then I'm going to go to the theory that I get by introducing the vector multiplet and thinking of it as a gauge theory, but with the gauge coupling equal to 0. And then I'm going to fully gauge it by turning on the gauge coupling. And from the point of view of the Hall-Littlewood chiral ring, what's going to happen is that I start out with the original Hall-Littlewood chiral ring, which I'm taking as a given. And then I'm introducing whatever the Hall-Littlewood chiral ring associated to a vector multiplet is as a tensor factor and projecting onto G invariance. And then I'm turning on a gauge coupling and seeing what happens. And the non-trivial step is the last one, where what happens is some sort of multiplet recombination, generalizing what I was describing in the hyperkähler quotient case. So I previously described that you have some removal of an ideal from the Higgs branch chiral ring because you had some moment map operator which became a supersymmetric descendant after turning on the gauge coupling. I'm going to have a similar story here for what controls the structure of non-zero coupling. And it turns out that the way that these recombinations can work is strongly constrained by superconformal representation theory, as is everything else. So I don't want anyone to focus on too much of these diagrams, except to say that the way that these sorts of short BPS multiplets can be recombined into non-BPS multiplets when I turn on the gauge coupling is restricted to happen in one of a couple ways. And in each case, if you look at both of these little diamonds that I've drawn, which corresponds to quartets of BPS representations that are getting recombined, in each case, the Higgs chiral ring multiplets, the B hats and the D bars, are appearing connected by this one supercharge Q1 minus. And so there's a single supercharge named Q1 minus whose effect as I turn on the gauge coupling is controlling the way that operators are removed from the spectrum of this Hall-Littlewood chiral ring. And this gives me a cohomology problem. This Q1 minus action is something that now is going to be defined on my 0th order Hall-Littlewood chiral ring as a differential. And taking the cohomology is going to remove all of the things that recombined. And the cohomology problem looks like this. So the Hall-Littlewood chiral ring associated to just the G vector multiplet is a Grassman algebra generated by these gauginos. So that's the exterior algebra on the Lie algebra G for the Lie group capital G. And my Hall-Littlewood complex on which my cohomology is defined is just my original Hall-Littlewood chiral ring tensored this exterior algebra projected onto G invariance. In the case when my original theory already had non-trivial sort of higher U1R grading pieces, then the cohomological grading on this complex is going to be the sum of the grading that I have on my pre-existing piece and the grading that I have on this exterior algebra. If in my original theory, the Hall-Littlewood Chiral Ring was just the Higgs branch chiral ring, as is the case for free hypermultiplets, then I get all of my cohomological grading from this exterior algebra. And then you just check in the interacting theory at a classical level, because I told you this thing is coupling independent and classically exact. You check how this Q1 minus supercharge works in the interacting theory. And it turns out that its transformations on the various ingredients in this complex are just things you can read off. I'm going to define the action of this Q1 minus to give me a differential called D sub HL. And for things in the Hall-Littlewood ring that I inherited, the differential is just 0. And for the gauginos, they give me the moment maps. So this is exactly the action that I was using to get the hyperkähler quotient before, only now I'm extending it to an action on this entire complex where I have the full exterior algebra. And then the cohomology of this thing is what we're looking for. It's going to be the Hall-Littlewood Chiral Ring of the theory that we get after gauging. And the Poisson bracket that you inherit is just such that these gauginos commute with everything, Poisson commute with everything. And you can check that the Poisson bracket still obeys the Jacobi identities when you do that. Okay. So this cohomological construction, which was just hand fed to me by the sort of structure of superconformal representation theory and gauging, is actually a natural operation from sort of a more formal mathematical point of view. Before taking into account the restriction to G invariance, this complex that I've defined is exactly the causal complex associated to the moment map. So what I'm doing is looking at some sort of G invariance of the causal homology associated to the moment map of this theory. If you're a physics person at all, then at this point, you might be tempted to introduce some things that you would call ghosts that live in the exterior algebra of G dual and turn this into a BRST complex. The causal complex is the first step to getting BRST cohomology in the classical sense of Costant and Sternberg. Interestingly to me, although at least some people one person I've talked to, I don't know if David Bensby is watching, but he told me not to be surprised by this, but it was surprising to me. Physics is dictating not to do that. If you really want to force this construction to live in the world of BRST cohomology, you can define a kind of relative BRST complex. But really, what you want to be doing is taking the causal complex and projecting to G invariance. And in contrast to what I would think of as sort of the usual applications of BRST that show up in physics, at least in my physics, which might be sort of lowbrow, here we're especially interested in higher cohomology classes that are coming out. So at least when you learn your textbooks BRST for gauge theories, you learn that the point is to compute H0. But here I'm exactly interested in the higher classes if I want to see sort of the stuff that makes the Hall-Littlewood Chiral Ring more than the Higgs branch chiral ring. And then the claim, and this now is really just going to be a slogan because I'm not going to have anything to do with it. But the claim is that what we're really doing here is the derived symplectic quotient in the sense of derived algebraic geometry. So I've read some papers by Pavel and probably even other people who might even see this at some point and I'll be embarrassed. But what's going on here is this causal complex that I'm introducing is what I'm really doing is introducing sort of the derived critical locus associated to the moment maps. And then I'm taking the G invariants, and you could phrase that in a more derived way, but it doesn't get you anything. So the slogan here for anyone who tuned in because of the phrase derived Higgs branch in the title of my talk, the slogan here is that if you didn't know about the virtues of derived algebraic geometry and derived symplectic reduction, et cetera, it's being handed to you by physics here. And you're not introducing anti-ghosts by hand because they make the formal structure nicer. They're there for you already in the physical fields of your theory, which I think is one of the remarkable things. In the usual story of BRST and Gates theories, you introduce ghosts and anti-ghosts as formal devices in order to make your gauging more convenient. Here, they're already there in your theory as physical fields, or the anti-ghosts are at least. Okay, so that's a slogan. I get a little bit of mileage out of some formal properties here. I guess I'm probably running over time, Tutor. How much leniency do I have from you?
-2 minutes.
Right, but how much leniency do I have from you?
You should wrap up fairly soon, just because this is a sort of formal seminar, and then we can have Q&A later.
Okay, let me bring up this full slide. So roughly speaking, and this is an area where I think there's more to understand, at least for me from a physics point of view. Roughly speaking, when you get these higher causal homology classes showing up, it's related to the failure of the moment map ideal to give you a complete intersection in your original construction. And because of the way the hyperkähler quotient works, the failure of the complete intersection criterion on the moment maps pairs with a failure of the G orbits to be full dimensional. And so you get a positive finite dimensional stabilizer of the G action on the zero set of the moment map, which is why I claimed at the beginning that what you're really probing from a physics point of view when you look at this extra structure is something about unbroken gauge symmetries on the Higgs branch. So it's some finite dimensional stabilizers, which is just another name for unbroken gauge symmetries. And so that corresponds to this picture that I had of mixed branches. So really the claim, if you're a less fancy person, the claim here is that you're gonna see these Hall-Littlewood chiral rings as something which is more than just the Higgs branch chiral ring, precisely when your Higgs branch really lives in some bigger geometry. So this is a thing where if you're cognizant of the full geometric structure of your theory, this is sort of an obvious property to pay attention to. But if you were just studying sort of pure Higgs branch stuff, you might not notice it. And here, by being sensitive to the full sort of derived structure that you get when you do the Higgsing, you automatically see this sort of embedding of your Higgs branch into a bigger mixed branch. And this leads to a reasonable conjecture, which doesn't turn out to be quite right. And I'll leave it, I'll finish by stating the conjecture and then stating in summary the way that it fails in examples. So this is, I claim this is a natural conjecture, but of course it's not going to be natural without some extra technology. So I claim that from sort of an effective field theory point of view, which some people in the audience will have a sense of what I'm talking about, that a natural conjecture for what this ring structure should be in terms of this full moduli space geometry is something like the coordinate ring on the parity shifted normal bundle to the Higgs branch inside of this mixed branch. So there's some extra geometry, and so you can sort of see that geometry, but only in in a parity shifted way, only sort of in an infinitesimal fermionic way. That turns out to be almost true in a large class of examples, but not exactly true. And so I'm just going to jump to the results. So now I'm jumping ahead a bunch of slides, but I'm trying to be faster. So with a fair amount of work, you can compute this structure for an infinite class of examples, which are the so-called class S theories of type A1, which are Lagrangian theories. And so there's some well-defined cohomology problem to solve, but you still have to solve it. For the class S theories of type A1 corresponding to a genus G Riemann surface, the Higgs branch, as computed first by, I think, Ami Hanani and collaborators, is the Kleinian singularity C2 modulo binary dihedral group, DG+1. And I claim that if you use this sort of normal bundle perspective that I was suggesting, then you're going to consider an upgrade of this orbifold description to a super orbifold, where instead of C2 modulo D type Kleinian group, you have C2/G super vector space modulo the D action, where you've upgraded the DG+1 action on C2 to act on the odd directions in a particular way. Now, somewhat amazingly to me, this prescription fails to correctly reproduce the Hall-Littlewood Chiral Ring, but you can fix the result just by crossing out some elements of your ring. So there's some extra stuff that you get from this orbifold picture that I think you should think of as operators that you can construct in effective field theory that don't make sense if you try to extend them back to the superconformal point at the origin. But that's a somewhat vague idea. Something that you see in this construction, if you had had time to stare at it, is that you get a large extra symmetry that acts on the fermionic degrees of freedom in this construction. So in this case, the Higgs branch has no isometry group, but the Hall-Littlewood Chiral Ring actually has a UG symmetry group that acts only on the higher cohomology. Okay, I've abused my host's patience more than I should, so I'll end on the last slide without reading any of the words, and people who want to read them can read them, and then we can turn to questions. Sorry for going over time.
Thanks very much, Chris. If anyone would like to ask questions, please raise your hand. While you're doing that, I will ask one. Is there a cohomology problem that defines the Hall-Littlewood Chiral Ring itself?
No. Well, no. I mean, okay. I should say that not that I can identify in any of the usual using any of the usual tricks. If there may be something fancier than I can think of. This is as you probably know in asking this question, this is like an old funny puzzle that the n=1 chiral ring of a 4D superconformal field theory is not actually defined in the usual cohomological way. And by specializing to, so this is true for the Higgs branch chiral ring, it's true for the full n=1 chiral ring, and you don't solve this problem by specializing to the Hall-Littlewood chiral ring. Something which I think has been maybe going on a little bit in the comments, although I couldn't follow it in real time, is that if you're willing to embed this Hall-Littlewood chiral ring in a bigger structure, there's a vertex Poisson algebra that is defined as the cohomology of a particular supercharge, which is sort of the semi-classical limit of the vertex algebra that I've written lots of papers about. The vertex Poisson algebra was described in a paper by G1, O, and Junya Yagi. So that thing is defined cohomologically, and it's graded. Unlike the usual vertex algebra, it has an exact SU2R and U1R and conformal dimension grading. And the Hall-Littlewood Chiral Ring is just a graded subring of that. So if you restrict to operators that obey certain grade restriction rules, then you can get the Hall-Littlewood Chiral Ring that way. So in some sense, by expanding the scope to a much bigger thing, you can get something cohomologically.
Thanks, Chris. Abusing my privilege as a host, the answer is different in 3 dimensions. So the Rosansky-Witten twist of a gauge theory does naturally carry gauginos that correspond to your derived structure, and gets this derived quotient on the nose. All right, let me go on to Sasha's question. Please go ahead and unmute yourself.
Yeah, thank you. So I have the following question. So you mentioned that the Higgs branch is essentially the same in 4 dimensions and 3 dimensions, and that in this talk you're going to take a 4-dimensional point of view. But what happens if you try to take the 3-dimensional point of view? Because I mean, your message in the end was that this ring, this Hall-Littlewood ring, is this derived Higgs branch, which is sort of, well, at least for Lagrangian theories, it is defined in terms of this derived Hamiltonian reduction, and that particular procedure somehow is sort of the same for well, it doesn't know about 3 dimensions, 4 dimensions. So suppose you just do the same in 3 dimensions. So that does the result make some kind of interesting sense in terms of 3-dimensional theory rather than in terms of 4-dimensional theory?
I don't know the answer. I think that Tudor was saying a comment that has something to do with this question, although I'm not sure I agree with exactly what he was saying from my point of view. Yeah, I think that this is a question that I find interesting, which is that on the one hand, if I pay attention to my derived algebraic geometry friends, they'll tell me you should always do derived Hamiltonian reduction. You should always do derived symplectic equations just because derived algebraic geometry is better. On the other hand, I have to ask, given a superconformal field theory with all of its extra ingredients, what falls out when I try to build a nice, subring of the operator algebra, which is specified by, having a partition function that computes its character or something like this. And in this case, there seems to be a dimension dependence in what you get. And I don't have a deep thing to say about that, except that I think it's interesting.
Dylan?
Okay, I just wanted to ask, for a general mixed branch, like what's the expected relationship between the 3D and 4D mixed branches? Like you said, sort of Higgs is the same, and of course we all know like Coulomb, there's like this integrable system of, one over the other. But like, what's the expectation for the general ones?
I don't think I have something smart to say here. I mean, it's you're gonna have something, at least in the sort of universality class of this kind of integrable system structure, because you're still gonna have. I mean, for example, in this mixed branch, in this extended Higgs branch picture that I had, where you just have a billion vector multiplets sitting over generic points on the Higgs branch. If you sort of do if instead of reducing and then looking at the moduli space, you sort of go out in the moduli space and then reduce, then you're going to get this this sort of torus vibration over that mixed branch. In this case, everything is abelian there. So you're going to get something which doesn't have a lot of extra sort of singularity structures. But then over the intermediate mixed branches where you're going to have some sort of residual interacting theories with some non-abelian maybe Gates theories that aren't Higgs, then you're going to have some more structure. And Jacques says something which hopefully is more lucid than what I'm saying. Wherever you have unbroken abelian gauge fields, these will become scalars in 3D. Yes, that's true. But then there's going to be some more intricate structure in sort of the way that the various singularities nest inside of each other. Sorry, I don't think that was a very good answer, but that's the best I can do.
Yeah, all right, thanks. And by the way, I just wanted to comment maybe the distinction between like what like tutors comment and your expectations in this 3D situation, like whether or not you see certain derived things, like it might just have to do with whether you think of treating your theory like using BV or not. Like maybe some people have some idea, like, you know, there are more or less fields involved. I don't know. Maybe I don't exactly understand what was motivating your expectations, but for me, I think that's sort of what I would say.
Yeah, I've run into this stylistic issue in previous discussions with Kevin, for example. But I mean, certainly there are some things which are supposed to be unambiguously defined, like the Hilbert space of your theory defined on a two-sphere, which is in a superconformal theory in 3 dimensions, the same, that's the Hilbert space of local operators. And I don't think you get to add stuff to that by doing a different quantization method if you want.
Sure,
so
yeah.
The question of whether you have, some, you know, 3/8 BPS analogs of these D bar multiplets in the 3D case is unambiguous, and I claim you don't have them.
Okay, I didn't totally follow, but I believe you. Thanks.
Any other questions for Chris? Yes, Cyril.
Hi. When you have still some residual SCFT at every point on your Higgs branch, how does it affect your story?
Yeah, that's a great question, and the answer is that if that residual SCFT has its own Hall-Littlewood Chiral Ring, which is non-trivial, then sorry. Maybe I should draw a little sketch for people who don't know what this question is about. So maybe I won't draw the picture. I'll just say extra words. I had described the sort of diagnostic for getting this extra derived structure as, from a moduli space point of view, being that you have the Higgs branch. The generic point on the Higgs branch actually has this sort of mixed branch structure in its neighborhood. But I was a little bit deliberate about saying that I wanted the Higgs branch to be sort of smoothly embedded inside of this mixed branch. There's another thing that can happen, which happens in a large class of examples, although I don't think I know every example where it happens, which is that if you look at the physics of a generic point on the Higgs branch, there's a non-trivial interacting superconformal field theory, which itself has no Higgs branch as the theory there. So there's a bunch of so-called Argyros-Douglas type theories where this happens. And the examples where this happens that I know of, you don't end up with any derived structure in the Hall-Littlewood Chiral Ring. In other words, the Hall-Littlewood Chiral Ring is the same thing as the Higgs branch chiral ring for those theories. And I would attach that fact to the fact that those residual theories that are left over on the Higgs branch themselves don't have a Hall-Littlewood Chiral Ring. So the special case of these enhanced Higgs branches is saying that sort of you have a residual theory sitting on a generic point on the Higgs branch that theory is the theory of abelian free vector multiplets. And the theory of abelian free vector multiplets has a Hall-Littlewood Chiral Ring, which is just an exterior algebra on the on the torus, on the algebra of the torus of those abelian gauge groups. There might be out there in the sort of landscape of n=2 theories, there might be situations where you have a residual isolated interacting SCFT that has some Hall-Littlewood structure, in which case my answer would change. But it's not, I'm not sure what's possible.
Thanks.
Well, thank you very much, Chris, and thanks to everyone for the questions and participation. Let's thank Chris again. And we'll stop the recording.